SPMT and SFMT as defined below are the phase modulated and frequency modulated waveforms respectively corresponding to the message signal MT shown in the figure. SPMT is equals to cos 1000 pi t plus kp times mt and SFMT is equals to cos 1000 pi t plus kf times integration minus infinity to t m tau d tau. Here Kp is the phase deviation constant in units of radians per volt and Kf is the frequency deviation constant in units of radians per volt second. It is given that the highest instantaneous frequencies of SPMT and SFMT are equal, and what we need to calculate is the ratio Kp by Kf in units of seconds. Also given in the question is the plot of MT with respect to time t. The NPTEL video reference for this question is Lecture 28 Principles of Communication Systems 1 by Professor Aditya K. Jagannatham, Department of Electrical Engineering, IIT Kanpur. Some useful information required to solve this question is definition of instantaneous frequency. For a generalized signal St is equals to A cosine theta t, where theta t is the angle of the signal, instantaneous angular frequency is defined as the slope of angle taken over a very small interval of time. Dividing instantaneous angular frequency by 2 pi, we get the instantaneous frequency of the signal. Phase modulation is defined as the type of angle modulation in which the angular argument theta t of the signal St is changed in linear proportion with the instantaneous value of the message signal MT. As can be seen from this equation, as MT varies, the angle theta t also varies in direct relationship. Frequency modulation is a type of angle modulation in which the instantaneous frequency changes in linear proportion with the instantaneous value of message signal MT. As can be seen from here, if message signal MT changes, the frequency of the signal also changes. We also need to know the mathematical definition of instantaneous frequency is Fi is equals to 1 over 2 pi times d theta I over dt. Here theta I is the phase angle of the corresponding signal. The term inside the parenthesis of this signal is its phase angle. We can denote it as theta I pm. We can utilize this phase angle to calculate the instantaneous frequency of this signal Fi pm, which can be written as 1 over 2 pi times d theta I pm over dt. Now we can substitute the above angle in this equation. We need to differentiate this equation once with respect to t. What we see is, in order to obtain the maximum value of instantaneous frequency, we need to maximize the derivative of the message signal MT. So Fi pm maximum can be written as the maximum value of the derivative of message signal can be obtained from its given plot. Derivative of a piecewise linear signal can be obtained simply by calculating its slope over the interval in which the signal is linear. We can write the slope between 2 points as V2 minus V1 by T2 minus T1. Here, V and T are the corresponding values on voltage axis and time axis respectively. We can now calculate the value of slope for different intervals of time. For t less than 1, the value of slope is 0 minus 0 by some time t, which is equals to 0. and corresponding derivative value is 0. For t between 1 to 3, corresponding slope value is 10 minus 0 by 3 minus 1, which is 5. Corresponding derivative value is 5. For t between 3 to 6, the slope value is 10 minus 10 by 6 minus 3, which is equals to 0. Corresponding derivative value is 0. For t between 6 to 7, slope value is 0 minus 10 by 7 minus 6, which is equals to minus 10. Corresponding derivative value is minus 10. For t greater than 7, slope value is 0 minus 0 by some time t, which is equals to 0. Corresponding derivative value is 0. We can now utilize these values to plot the derivative of the message signal mt with respect to time t. We now plot the derivative of the message signal. As can be seen, for t less than 1, the derivative has 0 value, so we plot it to 0. For t between 1 to 3, the derivative has a value of 5. We plot it to 5. Between t 3 to 6, derivative has a value of 0. Between t 6 to 7, derivative has a value of minus 10. And for t greater than 7, derivative takes a value of 0. As can be seen, the maximum value of the derivative is 5, which it takes between t 1 to 3. We can now calculate the maximum value of the instantaneous frequency of the phase modulated signal as FIPM max. Here 5 is the maximum value of the derivative of message signal, as can be seen from this plot. We label this equation as equation number 1. We can use the phase angle of the FM signal. Let's denote it as theta I FM, and we can utilize this to calculate its instantaneous frequency FIFM as differentiating this equation with respect to t, we get what we see is, in order to maximize the instantaneous frequency of the FM signal, we need to maximize the given message signal mt. We can write the maximum instantaneous frequency FIFM max from the given plot of mt. We see that it takes a maximum value of 10, and we can substitute this value in this particular equation. We obtain this equation. We label this equation as equation number 2. Comparing equations 1 and 2, we get we can eliminate 1000 pi by 2 pi from both the sides. What we get is 5 kp is equals to 10 kf, or equivalently kp by kf is equals to 2, which was asked in the original question. So our answer to the question is 2 seconds.